Question 11, we have iron 3 oxide can be reduced to iron using hydrogen. We have our equation and we've got the delta HF. Enthalpy change in for delta H naught in kilojoules per mole for the reduction of iron 3 oxide using hydrogen. So we are going to use the equation which you're going to lift straight from your data book. So delta HF of your products minus delta HF of your reactants. And that's it, you're just going to plug this in. Okay, so products is these two, so I'm looking for 2 times this and 3 times this. So I'm going to just ignore my zero number. Okay, so minus and our reactants, just making it clear. Okay, oh no, I thought I changed my colour. I changed my colour. So I've got 1 of these and 3 of these, but obviously another 0. So I'm just going to put minus 822, and that's going to come out as plus 96, and that's us. Okay, which line in the table is correct for water condensing? So we've got the delta H and we've got the delta S. So what we're doing if we're condensing water is we're taking it from a gas form to a liquid form. Right, so let's start with what's happening in terms of chaos, disorder. Okay, this is high disorder because we've got a gas, and this is not so much disorder, so lower disorder because we've got kind of connected molecules in the liquid. So our delta S is going down, so we've got a negative delta S. Okay, so our delta H, so the energy inherent in the actual system. So if you think of that just on the kind of normal kind of energy scale, our gas is going to be up here and our liquid is going to be down here. So again, dropped, and that's it. The results in the table were obtained for this reaction. X plus 2y gives you Z. You've got data for this one. The results, from these results, the rate equation is, okay, right, so you've got to take pairs to figure out what's going on. So let's take the first one just as your standard. So 0.03, 0.03, giving us 0.0064. In experiment 1 to 2, I have doubled X, kept Y the same. So if I've doubled this, what's happened to the rate has also doubled. So that tells me the X, if I'm doing my rate equation, making my K look little, I have X is definitely in the rate equation with a 1, okay, first order. You don't have to put the 1 in though, okay? And then we look at number 3 in comparison to 1 and look at what's happened. So what we've done is we've kept X the same and we have halved our Y. So this is gone, this is halved. So if this was proportional in terms of to the first order, then we would expect it to half the rate. But however, if you look at the rate has remained exactly the same. So therefore, basically this is not in the equation. You could put it in as that, but that's not an option in the answers, okay? So, and A. Right, okay, we're looking at rate constants and units for, and I must admit I don't like these, but it's just something you need to know. So the rate of a chemical reaction is second order overall. The units for the rate constant KR. Now, you can either, now I've pulled this is the statement. It says the rate equation and the rate constant, including units, can be determined from initial rate data for a series of reactions in which the initial concentrations of reactions are varied. Well, that's effectively the rate equation bit was question 13. These can be 0, first, second or third. So they're saying that you have to be able to do the rate constants all the way up to third order. Now, I personally go with just learning them. So first, 0th order, would be liters to the minus 1 mole per second, and then we've got just per second. And we've got litres mole to the minus 1 s to the minus 1, and then we've got litre squared mole to the minus 2 s to the minus 1. Now, I can see a pattern in that with my L's and with my moles, which gives me it as a way to remember it. But if you can't do the pattern, then you have to be able to do, it does say determined, and that means you would have to derive it. So for second order, what you'd be looking at is saying that rate is equal to k with whatever you've got squared. Okay, it might be like an x to the 1 and a y to the 1. The whole point is that we've got two concentrations involved in this to get second order. Okay, so what that means is that we could rearrange for k to get the units, and so therefore we've got rate over x squared. Okay, and so that means that we are looking at our rate is going to be in concentration per second change. So if I just go with as in molarity per second, and then I've got our concentration below, so that's going to be molarity squared basically. So I need to cancel off one of these, which is why I go to a 1 over s here, and I'm still left with a 1 over our molarity down here, which is why it's this one. Oh, making a little bit of a mess of my little scribbles. Okay, so B. I don't like it, but it is what you have to deal with. Okay. Right, question 15. We've got the structure of 2-furanitrile shown below. The number of pi bonds in it is, now actually I think this is easier than it looks. Okay, so pi bonds, remember that for every connection has to be a sigma, and then every double or triple off that has to add in a pi bond. So one of these in here is a pi, one of these in here is a pi, and then we've got 2 pi's, one on either side of this one. So 4. Done.